Let's begin. Welcome again. Third lecture, CFD, and I promised you in 4 lectures you're going to have CFD code running. So the last 2 lectures don't really count because one of them was introduction and me blabbing about how awesome CFD is. The second one was reminding you of the equations, which you should know, right? So really we start today. So in 4 lectures from today, 4 to 6 lectures, I hope we have a CFD code up and running. Today we're going to get our hands dirty with coding. It will be baptism with Python, okay? So we're just going to get in whether you know Python or not. There's no stopping us. We're going to keep moving. You copy what I'm typing, and then you think about it later. So I'd like you to at least have your Jupyter notebooks turned on just so that when we are ready to start coding for you, okay? So far, we are at a point where we have a working set of equations. And I said we're going to focus on the 2-dimensional, incompressible, laminar flow equations. Those are the simplest equations. And frankly, the level of complexity in these equations is sufficient enough to get you started on adding more CFD. So adding turbulence to these equations is not a very big deal if you know how to solve these equations. So let's learn how to solve these equations first. We'll add the embellishments later, okay? First, however, I don't want to approach those equations directly as is because they look pretty scary and all nasty, and there's no clear way on how to untangle the pressure from the velocity, like I've mentioned a few times. Like there's no equation for the pressure again. So what I want is to set up a toy model for these equations, and the toy model should be simple enough that we can actually focus on the numerical methods that we will end up using on Navier-Stokes. So we will use the toy model to introduce the numerical methods, the pitfalls of the numerical methods. So the way we're going to turn these equations into algebraic equations that we can solve and get numbers. We'll play around with that. We get familiar with the numerical method. Then we take that numerical method and we apply them, or those methods, and we apply them to these equations. So what kind of toy model do we need? I know you can tell as there's advection, diffusion, and sources, but I want to drive that point home because I want to use that nomenclature later. So I want to write these equations in vector form, okay? So again, if we assume that our velocity vector field is given by this u velocity vector field, function of x, y, and time. The x component is axial velocity u, y component is v. Then your continuity equation simply is a vector statement of the divergence of the velocity equal to 0. So that's du by dx plus dv by dy equal to 0. Now, the Navier-Stokes, the 2 momentum equations, the x and y momentum equations, the way I like to think about them is that whatever is in the time derivative is the quantity that is being transported and moved around in space and time. So for the x momentum, it's the u velocity, which is momentum per unit mass, right? The u velocity is the quantity being transported in the x momentum equation. The v velocity is the quantity, or momentum per unit mass is the quantity being transported in the y momentum equation, okay? Now, you start looking at the different terms. These first 2 terms, like we said last time, those represent advection of the quantity being transported. And advection is a process where things move with the fluid velocity. So what is the fluid velocity is u and v. So you see u and v over here. What are they transporting? They're both transporting u, okay? So this is nice. It's kind of clean when you think about it this way, that I'm transporting u with u and v in both x and y. So you always see with the advection term, it is always a first derivative, okay? And we can write this in vector form very cleanly as minus div of vector u times scalar u, okay? So this is the x component of velocity being transported by the velocity vector. Now, if you expand this with vector calculus, you just get duu by dx plus minus dvu by dy, okay? And same thing for the y velocity component. The quantity is y momentum per unit mass, which is v, and it's transported by u and v, by the both velocity components. This is the transport in the x direction, convection in the x direction, convection in the y direction, all right? So first derivative, now start thinking that first derivative always indicates advection, okay? And that term is written similarly, minus div of u, the velocity, the velocity that's transporting information. Information in this case is y momentum per unit mass, which is v. Okay? Now, for the second derivatives, if you're a chemical engineer, you've probably learned that second derivatives designate diffusion. If you're a mechanical engineer, you recognize this from heat transfer, which is also a diffusive process. So this would be our diffusion term for the x momentum component, which is x momentum per unit mass, which is u, right? And you can write this in vector form as, mu over rho times the Laplacian. This del squared is div of the gradient of the x component of momentum per unit mass, which is u. So del squared u is d2u by dx squared plus d2u by dy squared. Okay? Same thing for the bottom one. You have your diffusion of y momentum. And then here you have a bunch of source terms. Those, they stay as they are. They're forcing terms. They're driving forces for, if you remember when we derived the advection diffusion equation, we had source terms, which are external driving forces that act either on the volume or on the surface of these fluid molecules to kind of move it around. Now, when you put this in vector form, you can consolidate both equations, both momentum equations, into a single vector equation. Again, remember, the u velocity vector has two components. So these are two equations, and this would be uv. Now, this one is interesting. You have div uu. Okay, this is not u squared. U, two vectors next to each other, is actually a tensor. Okay, so it's not a product. It's just u. And the way to think about it is, let's say this u is the quantity being transported. So make it here. So if this becomes the axial momentum per unit mass, so lowercase non-vector u, so x momentum, then replace lowercase u over here. You still have the vector be transporting x momentum, but you only change this one. Same thing here. And then you have the x component of gravity. For v momentum, you just put v over here. You still have div u vector of times v, right? And then you can get the other equations. But this is kind of nice and compact because it tells us directly that this term describes a physical process. This is another physical process. This is another one. And those are our sources. Now, I told you there's no equation for the pressure. But later, we will learn how to convert the continuity equation into an equation for the pressure. And without going into the nasty details, you will know that div u equals 0 is converted into a Laplacian of the pressure equals some source term. Okay, so del squared p equal s. This is called the Poisson equation. Okay, if s is equal to 0, it becomes Laplace's equation, del squared p equals 0. But in general, del squared p equals something. And that thing we will derive later is related to convection and diffusion. Okay? All right, so these are the equations we're going to be dealing with. Again, I'm trying to set the stage for a model equation that is linear and that is simple to deal with, so we can focus on numerical methods, on learning how to apply numerical methods to these types of equations. Right? So this first term describes unsteady effects. We call it transient term. I didn't want to call it transient term. I want to call it unsteady effects. So it describes the change in time. Right? This first term describes advection. So it is the transport of a quantity under the time derivative with a velocity vector field. So this u corresponds to this u, and this vector u is the same. It just happens to be the same, right? If this was another quantity, if you remember advection diffusion equation, if this was phi, then you just put phi over here, but you still have u for advection. Okay? This would be diffusion, and then you have a bunch of source terms. And finally, this is called the pressure Poisson equation. It's a Poisson equation. It also describes steady state heat transfer. Come on. It also describes the steady heat diffusion. Okay? So steady state heat diffusion, this is the equation for it. Okay. So to solve these equations, we need to first learn a few things. We need to learn how to approximate the time derivative, how to approximate spatial derivatives. So if you think about this, we have a time derivative here. We have space derivatives here. If you remember, this is duu by dx plus duv plus dvu by dy, etc. This also has spatial derivatives, but they're second derivatives, right? This has a spatial derivative in it, right? Okay, so we need to learn how to approximate spatial derivatives, and finally, how to solve a Poisson equation. Okay, so I need a model equation that will allow us to do all of these things. We're going to do them one at a time, start combining them, looking around and kind of exploring the space. And then we have to do this both in 1D and 2D. Because we're going to come out of this course knowing how to do two dimensions. The nastiest one is going to be this one in 2D. Okay, not impossible. This is going to take a little bit of work. Okay, at least programmatically, it's doable nicely, but it's going to take some finagling. All right. Okay, so a toy model for Navier-Stokes is kind of obvious, right? Because you have advection and diffusion and sources. So a great toy model would be simply the advection diffusion equation, which we studied and learned in the last lecture, right? It's transporting a quantity phi, whatever it is. Could be temperature, could be energy, could be velocity. It's just some dummy variable transported by some velocity vector field. We are going to prescribe that right now. We're not solving for it. We're going to prescribe it. We're going to say the velocity is 1 meter per second or 10 meters per second, okay? And it's transporting phi by advection, transporting phi by diffusion. This is diffusion coefficient with some source terms, okay? And we need to do this in 1 and 2 dimensions. Okay, great. So that's what we're going to be after in the next 2 to 3 lectures, is to solve equations of this type in 1D and in 2D. Now, when this is steady, so there's no time-dependent term, and there's no advection term, this automatically becomes a Poisson equation. Okay, so we're going to do that as well. We're going to do it in 1D first, and then the 2D will be the last thing we're going to do for that equation. Okay, so if you go back to the first set of slides, I said after we develop the mathematical model, right now we have a model. It's called the advection diffusion equation. So we're going to work with the advection diffusion equation. We need to define, we need to solve these equations numerically, and that step we call discretization. We will learn to discretize initially with the finite difference method, FDM, and later on we will learn the finite volume method. So we will do the finite difference method on advection diffusion, and then on Navier-Stokes, and we will learn how it fails miserably on Navier-Stokes. Well, it works, but there's an issue with it. Then that sets the stage for the finite volume method and what we call the staggered grid. And then, so the finite volume method, we're going to do it automatically on the Navier-Stokes. But then you can easily apply it on scalars as well, on the advection diffusion. All right, what is the finite difference method? Mr. Leonhard Euler, I don't know why I mean, he was like, okay, important in the development of calculus and infinitesimal calculus, but I just like this guy. He looks like very, Mona Lisa-like, and he's probably like very sleepy. Look at his eyes, like, I did so much math today. My brain is like completely collapsed. Yeah. Anyway, okay. So the goal of the finite difference method is to approximate derivatives. That's all there is. And you probably know these equations that the approximation to the first derivative is this rise over run in the limit as the run shrinks to 0, as the spacing between the 2 points goes to 0, you recover the exact derivative. But, we're going to be converting. We need a mechanism to convert continuous terms. Remember, we have advection diffusion and all of these derivatives. We need, all of them are partial derivatives, first and second. We need to convert them to things like this. Because once we convert them to things like this, then we can develop systems of equations with these unknowns and just solve those systems of equations. Okay, now what do we mean by an approximation to a finite difference? So initially, if you think about the finite difference method, if you had a known function or a set of discrete data values from experiments, for example, that's what we did in undergraduate numerical methods. This formula allows you to approximate the derivative of or the rate of change of the data. So for example, say you have some x and y data, I put them arbitrarily like this. You have these kinds of data, and the spacing is the distance between any 2 data points. Could be constant, could be not constant. Then you could say, well, the slope at this point, I'm going to approximate the derivative as the rise over run over here. So this value minus this value, so that's f of x plus delta x over here minus f of x over this distance between the 2 points. So the way I like to think about it, not in terms of nomenclature, x plus delta x minus f of x, as I say, this point minus that point over this point minus that point. So this over that, right? Rise over run, okay? Now in practice, you have data that looks like this. assume you have a bunch of data located at independent variables going from x1 to xn, and you have a bunch of values. I'm using u to enforce the idea we're doing velocity fields, u1 to un, right? This might not be new to you, so just bear with me. Now, we call these grid points. We call these discrete points, we call the grid points. We say this is the grid on which your data is distributed or exists. And in general, the spacing may or may not be equal. And then you could say at any point I, the derivative, like that same formula that I showed before, is simply the difference between two neighboring values over the distance between them. Okay? Now, notice that how I'm using this indexing here. Du by dx at I is equal to saying du by dx at xi. Okay? So that's the same thing. It's just easier to put the index like this. Okay? If the spacing is equal, then you have a single spacing between all of those points, and simplifies a lot of math. We call this delta x. Could be called h or delta t. Doesn't matter. Okay. Good. Now, the approximation uses points. This approximation uses points I plus 1 and I to compute this derivative. That's not the only way to do it, okay? But I'm using this now to define some nomenclature. Now, the fact that this approximation uses these 2 points, it could be using these 2 points, or these 2 points, or this, and this. We'll learn later how to derive different approximations. The set of points that you use to approximate a derivative is called a stencil. All right? So we call this a stencil. A stencil is the set of points that is used to approximate a derivative with respect to an arbitrary point I. It has a very strict, nasty definition, very mathematical, shown like this. Don't worry about it. Here are some examples. So let's say you want to approximate the derivative at point I using stencil points 0, 1. So that means you're going to use point I and I plus 1 to compute this approximation. And then this approximation is then formally defined as some coefficient times the value at ui, right? Those are our stencil points I and I plus 1. So I'm saying to approximate the derivative at this point, I only want to use I and I plus 1. Okay? So the answer is going to be some coefficient times ui plus some coefficient times ui plus 1. I could say I want to use a stencil that is more balanced between left and right and the middle. So a stencil that looks like -1, 0, 1 is equivalent to using I minus 1, I, and I plus 1, right? So you can see the pattern here. You're taking I and adding these numbers to it. Okay? And then the answer truly would be du by dx, the derivative at point I, is some coefficient times ui minus 1 plus some coefficient times ui plus some coefficient plus 1. How do you find those coefficients? You do Taylor series, etc. We're not going to get that. I'll give you these coefficients. We'll only be using a few of those coefficients, okay? But this is the general way of designing new finite difference approximations. Okay, you say, I want my approximation to look like this. Go find these alphas. Then you run this through Taylor series, and you come up with a system of equations for the alphas. They might be 0. They might not exist. Okay, there might not be an approximation, and those are all possible solutions for this. Okay. Now, to obtain other types of approximations, we can use Taylor series. And if you recall, the Taylor series of some function f of x around some point x naught is given by, so if you know information at x naught, okay, you can describe the function at some neighboring point that's a distance x minus x naught away from x naught. And this is an infinite series. The Taylor series tells you that the true function is equal to the value of the function at this point of interest, okay, plus the derivative at that point of interest times the distance between, the derivative at x0, that reference point, times the distance between that point of interest and x0, plus 1 over 2 factorial, the second derivative at x0, et cetera, et cetera. So this is based on the assumption that you know, so think of it this way, if you know all the information about the function at one point, so assume I know f and f prime and f double prime and all the way to the nth derivative of f, At one point x0, I can know everything about the function in the vicinity of that point. Okay? That's the power of the Taylor series. Now, we're not going to use it in this context. The way we're going to use the Taylor series, we're going to say, well, we actually don't even know what f prime is and what f double prime. We're going to find them. But we're going to use the Taylor series to mess with the derivatives, okay? To convert the derivatives, because this is a polynomial. It's x squared, x cubed, x to the power n, right? It's in a way simpler to deal with than a transcendental function, okay? Okay. And this is a very powerful statement because it tells you that any function in the world can be approximated as a polynomial. We say that the real space of functions, or the set of functions, the function space is dense in polynomials. Any point in the real space, if it belongs to a function, it also belongs to there's a polynomial that passes through that point. Okay, so this is a very powerful statement. Okay. Now, how do we do this to find finite difference approximations? It might be obvious for that first derivative that I showed you, but let's do it anyway. So suppose that you want to find an approximation to the first derivative. Okay? So suppose we want to find an approximation for du by dx at point I. Okay, so what you do in that case, you write the Taylor series at xi plus 1 in the neighborhood of xi. See how that's going to work? Because I am after f prime at xi. So if I write the Taylor series at xi plus 1 around xi, then I have f prime of xi on the right-hand side. See how that works? So u at xi plus 1, or u at I plus 1, in the vicinity of ui is equal to u at xi, which is ui, plus the distance between the 2 points, xi plus 1 minus xi, times u prime at xi, which is what I'm after, okay? And then so on and so forth. Okay. So for simplicity, I'm going to drop the xi plus 1 and xi. I'm just going to say ui plus 1. So ui plus 1 means u at xi plus 1, and so on. Okay? Okay, great. So now we have this formula, right? Our objective is to get u prime at I. Well, I have a formula that relates ui plus 1 ui, u prime I, but I have a bunch of derivatives here. Well, let's see what happens if we solve for u prime I. Just solve for it. Okay? Just solve for it. No mystery. Take it to the left-hand side, move everything to the right-hand side, see what happens. So you get, so if you take this to the left-hand side, move this here, cancel out, rearrange terms, do the proper sign adjustment, you get u prime I is ui plus 1 minus ui over delta x, which is our derivative, plus a bunch of other terms. Okay? But hey, we're working with approximations. So we're gonna say, you know what? We are mathematical dictators here. We're gonna neglect all of these terms. But you're gonna pay the price later for that, okay? You're gonna pay the price later. So because we don't know what those terms are, but if you knew ui plus 1 and ui, etc., you can completely compute this derivative with this formula. These are a bunch of terms we don't know. We can neglect them. We're doing approximations anyway. And then you say, well, the approximation to the first derivative using this stencil, 0, 1, looks like this. And that's, you know, our traditional famous formula. Now, if I go back here, and if you take the limit as delta x approaches 0, all of these terms will disappear. So this formula becomes exactly u prime, right? So that's what you learned in high school calculus or in numerical methods, for example. Okay. Now, all the terms that we neglected define what we call the truncation error. Again, I'm taking you in a little detour over here to introduce some terminology that's going to be useful later. Okay, when I say later, oh, the truncation error is causing this, you're going to remember, oh, the truncation error is the result of when we approximated an exact process with the Taylor series, whatever we left out, okay, is the truncation error. Everything you left out is called the truncation error. In this case, it's technically defined as the exact value minus the approximated value, right? So you get all of those terms. So u prime exact minus u prime I gives you all of those terms, right? All of those terms. That's the truncation error. Now, luckily, the truncation error, despite the fact that it has an infinite number of terms, it's always bounded by that leading order term, as long as the process is normal, is not unbounded, is not crazy, doesn't have shock waves, a bunch of weird things like, for normal, continuous fluid flow, right? Things that 99% of the cases is the case. Then this truncation error is bounded by that first term, because that term dominates. Now think about it. The next term over here has delta x squared. The next term has delta x cubed, etc. As you bring delta x to 0, as you shrink your spacing, then those terms are going to go to 0 faster than this term. This term is going to dominate. It's like you have 1 plus 0.1 plus 0.01 plus, right? That one is going to dominate. That first term is going to dominate, okay? It turns out that indeed the entire error is always less than whatever this, some constant times this first term, delta x, okay? Now, you might have seen this in math before or not. We say then the error, the truncation error, is of order delta x. It means in the limit as delta x goes to 0, the error is kind of parallel to the line that defines the slope that is equal to delta x, okay? As you shrink delta x, you have a line that's going down, and your error is going to be parallel to that. It might be a little bit higher, a little bit lower, but it's going to be consistent with it. It behaves in a way that is similar to that. That's what order means, the big O notation, we say. Okay, so we say that the error, again, I'm not talking about this in a very exact sense because it's not going to matter to what we're going to do. It's going to matter a little later where we're going to become more exact about our terminology. But I want you to hear it now. So we say that the error is order delta x. Now that's important because when I tell you my approximation is order delta x, that immediately says something about your error. If you cut your delta x by half, then your error is only going to be cut by half. Right? So let's say you are sampling, you're doing measurement of something, and you're doing it at some interval delta t, 1 second intervals, and then you approximate your data, the rate of change of your data, with a delta t process, okay, delta t approximation. Then you say, oh, I need more accuracy. So you go sample every half second. Then you know that your error is only going to be cut by half. You're not going to get much out of it, okay? That's a pretty useful statement. All right, and we'll see later how that works. And you can write u prime exactly by writing it equal to the approximation. See, this is an exact equal sign, plus order delta x. Instead of carrying all of those truncation error terms, you say, well, there's a bunch of terms here. The leading error is order delta x. So that's what we're going to do. Now, in general, an approximation is said to be of order p. Okay? Excuse me, if the truncation error is of order delta x to the power p, or delta t to the power p. So if p is 2, you say this is a second order method. If p is 3, you say this is a third order method, and so on. That's it. When you hear, oh, they use second order discretization, it's just they use an approximation to the derivatives that results in a truncation error where the leading order term is delta x squared. That's all there is, okay? Now that has implications on the error because the error for a second order method, if you cut the spacing by half, you cut the error by a factor of 4. So if now you approximate the derivative with the second order method, you sample at half seconds, you cut your error by a factor of 4. So you cut it by a fourth, right? So that's a lot. For a third order method, it's cut by an eighth. Okay? It's cut by an eighth. So that's the power of these higher order terms. Now this has direct implications also in practice on grid spacing. You're probably all familiar somehow with CFD, like a number. How many grid points do you pick? Well, it also depends on the accuracy you're seeking, right? For the first order method, 11 grid points, let's say on some domain that's of size 1, if dx is 0.1, then your error is on the order of 10% for a first order method. For a second order method, your error is on the order of 1%. With a first order method, to get to an error of 1%, you need to have 101 grid points. Okay, 10 times more grid points to get the same accuracy that you would get with 11 grid points in a second order method. Right? Pretty nice. Second order method with 101 grid points, you get to 0.1%. Okay? All right. So now let's do some a little bit of light math on this. if the error is, so when I tell you a method is of order delta x to the p, you immediately can say, oh, my error E, write the error, which is the difference between the exact solution and the numerical solution, okay, is equal to some constant times delta x to the power p. You can make that statement, okay? Now, if I take the logarithm of that, okay, whenever you see a power, it's nice to take logarithms. So you split the log on this. You get p log delta x plus log this constant c. And then just a little trick here. If I swap this, you do log of 1 over delta x, you get a minus sign, right? Because minus log 1 over delta x is log delta x. So it's still the same equation. Then this is the equation of a straight line in log-log space, right? The log of the error on the y-axis is equal to minus p times log of 1 delta x. So if on the x-axis you put log of 1 over delta x, that becomes your independent variable on the x-axis plus some constant. So this is the equation of a straight line. So the error, in other words, is the equation of a straight line on log-log space, okay, where the intercept is this constant, which really doesn't matter much. What I care about is the slope p, because that's usually what we are after when we are trying to verify a numerical method. So on a log-log plot of the error versus 1 over delta x, the order of accuracy p is the slope of the lines on that plot. So if I were to take a method, let's say first order derivative approximation, second order, or third order, and then I start changing my spacing, okay, make h or delta x smaller and smaller and smaller and smaller, and plot the error, you're going to get straight lines that look like this. The slopes of the lines are your order of accuracy. Now, this is not a joke. You see this in papers that we actually publish. And if you pick up any serious numerical paper or computational physics paper, I guarantee you that each and every one of those papers, they have a plot like this. I showed it to my students in numerical methods this year. I pulled up one of our papers. There's like 20 of these plots to demonstrate order of accuracy. Okay, we're going to get back to that later, okay, as a tool for verification. But I just want to introduce the nomenclature here. Okay. Now, we can obtain all sorts of different approximations by applying the Taylor series at different points and combining different Taylor series together. So far, we did I plus 1 and I stencil, right? So 0, 1 stencil for the first derivative. You can also do the first derivative with a minus 1 and 0 stencil. So I minus 1 and I. And in that case, you write the Taylor series at I minus 1 around point I. So you get ui minus 1 equal ui minus delta x u prime I, etc. So you need to master this, okay? As we go through the course, you need to be able to write these, just come up with them immediately, all right? Now you do the same thing. You approximate u prime. You solve for u prime. You neglect the high order terms. What you're going to get a backward difference, okay? You'll get u prime as another approximation of the derivative as ui minus delta x. It's of the same order as the previous method, but this one is biased to the left. That's very important, because this is the upwind scheme for flow moving. If you've heard of the upwind scheme, this is the upwind scheme for flow moving from left to right. The other one is the upwind scheme for flow moving from right to left, okay? So we will talk about upwind schemes later, okay? You can get a higher order approximation by combining ui minus 1 and ui plus 1 together. Yeah, if you combine the Taylor series of ui plus 1 and ui minus 1, you combine them together like this, you get another approximation for the first derivative, which is completely balanced from the right and the left. So the derivative at point I becomes a balance between I plus 1 and I minus 1, but it gives you second order accuracy. The error in this case is delta x squared. Okay, so you cut the spacing in half, you're going to cut the error by a fourth. But as you will learn in the upcoming lectures, a higher order method doesn't mean that you're going to get results that converge. We will see that when we apply this approximation to the advection equation, the results will be catastrophic. You cannot get a numerical solution, okay, because it violates the physical principle of advection, as we will see. Okay. I'm going to show you 4 approximations that we are going to use in the, if we start coding today, we will use those today. The forward difference formula, which is u prime uses I plus 1 and I. Backward difference uses I and I minus 1 for the first derivative. Central difference formula for the first derivative is I plus 1 minus I minus 1 over 2 delta x. Remember the spacing between the 2 points. And the second derivative, remember we have second derivatives for the diffusion term. Okay? So that also you do the Taylor series. We're not doing that here, but you can do the Taylor series at I minus 1 and I plus 1 and combine them this way, and then you can approximate the second derivative. Okay? So one trick to say, what Taylor series did they use here to approximate this? We use the Taylor series at ui minus 1, no Taylor series here, Taylor series of ui plus 1. If you combine them together, terms will cancel out, and you'll get the second derivative. Okay? Very simply like that. Now, these could be applied on time and space. So instead of delta x here, you could have delta t. Okay? So don't be confused when we have a time derivative. All right, finally, how is this helpful? So far, we saw how to find like approximate derivatives of known data, but we're after unknown data. We're after partial differential equations. Okay? So how can we apply these to solve differential equations given that we don't know the solution? Well, let's try. What the heck? Let's try to apply these finite difference formulas to differential equations. So first, we are going to chop up our computational domain into a set of discrete points. As a matter of fact, that's what we do in experimental data. We have a set of discrete points on which we compute the derivative. Well, let's make up a set of discrete points on the PDE that we're trying to solve. So we're going to take our domain. We're going to chop it into a set of discrete points. Let's make them equal for simplicity. Okay? The case for unequal spacing is trivial. Okay? Same thing for 2 dimensions. We will talk about 2D later. Okay? And then the next step is you assign value for the quantity that you are trying to solve. You assign a variable, not a value, sorry. You assign a variable name for each quantity that you're trying to solve at each grid point. So obviously, you need your abscissa, right? So the x values, x1, x2, and so on. So each one of those points has an x value. But also, we're going to assign to each one of those points an unknown variable name. So remember, I'm solving for the u values. I don't know what they are. But I know that they're going to live at those points. So we're just going to give them names. u1, u2, u3, all the way to un. Okay, same thing in 2D. Again, we'll talk about 2D later. Now, this is the critical step, is that now the governing equations, aka the Navier-Stokes advection diffusion, they're valid everywhere on that domain, the continuous PDEs. And therefore, they are also valid at the discrete points, because the discrete points are a subset of the full continuous domain, right? So we can apply the governing equations at each one of those discrete points. So I can apply my du by dt equals some right-hand side at point 1, and I can apply it at point 2, and I can apply it at point I at any point. Okay? Now notice I put a subscript and a superscript. The subscript designates the location in space, and the superscript designates the location in time. We haven't spoken about time yet. Okay, I'm not going to speak for a minute. So I put a question mark. I don't know what location in time this derivative is. But at least I know this continuous process is, this equation is continuously valid at each one of those points. So all I'm going to do is take it and apply it over there. All right? Okay, great. So next, the last step is to convert the derivatives into these algebraic relations and see what happens. Okay, now I cannot do this generically, so I have to do it by example. And once you do a few examples, you're like, okay, I know what's going on. And the trick is you approximate these derivatives with the Taylor series approximations we learned. And then what you're going to get relations between u1, u2, u3, u4, et cetera, a bunch of equations. You should have as many equations as there are unknowns, and then you can solve those. All right, let's do an example. So we will start with the 1D Poisson equation. Remember, we wanted to do the Poisson equation for the pressure. We're going to do that in 1D and 2D. So we'll start with 1D. And the 1D Poisson equation, the Poisson equation is nothing more than a steady state, heat transfer, or steady state diffusion. In this case, it's going to be 1D. And we will take a simple example that I use in my numerical methods course, which is the temperature distribution in a rod, in a one-dimensional rod, held at fixed temperatures on the left and on the right, and we have some air blowing at it at some ambient temperature T infinity. Okay. The heat equation in this case, you studied this in heat transfer. This is an advection heat transfer problem. For all you care about is that this is the governing equation for this problem. So this is indeed a Poisson equation in 1D. It's a second derivative with a source term. Okay. Now the source term has a bunch of parameters. H, which is heat transfer coefficient. P is the parameter. Lambda and the area. Bunch of parameters here. Times T minus T infinity. T is the actual temperature in the rod. T infinity is the ambient temperature. Okay. Now once T in the rod reaches T infinity, this becomes 0, and then nothing changes anymore. Okay, you reach essentially no more change in your heat transfer. Okay. All right. So I'm going to use this as a segue to start doing our discretization process. So this is going to check Poisson equation and 1D of our list at least. Okay. So let's do it. The first step is we discretize our space domain. It goes from, say, 0 to L. We're going to use L equal 1. Doesn't matter. Once we get programming, we'll put in some numbers just to make them make the numbers make sense. And this is fixed at temperatures on the left. I'm going to call it T left. On the right, I'm going to call it T right or T0, TL, whatever you want. Okay, but those are known. Okay, those are given to us. Yeah. Then we split the domain into a bunch of discrete points. Equally spaced. You could choose. You could say I want 100 points, 2,000 points, 15 points. Yeah, just put a bunch of points, okay, and then you can calculate the spacing in between them. All right. For simplicity, I'm going to make this equation. I'm going to call this parameter HP over lambda AC equal H T minus T. It's just a number. Okay. Now, physically, intuitively, if this number is high, it's going to diffuse heat very quickly. Okay, so we have the rod fixed at two ends here, but I have T infinity blowing, right? If H is high, it's going to make T infinity essentially just propagate very quickly throughout the rod. If H is low, it's going to be very hard for T infinity to make the rod kind of be at T infinity. And that's intuitively what we expect, right? Because when H is large, this is a huge source term, right? And when H is large, you're going to make this term just dominate this right-hand side. You're going to drive the heat transfer faster. All right. So the next step is to assign a variable name to each one of those points. So on the x values, I'm going to call them x values, right? So x1 is 0, x2, x3. They're just abscissae, or just the abscissae on this x-axis. And over here, I'm going to assign t1, which we know is equal t left. So I'm going to still keep it as part of my variable list. Because when I want to plot, I also want to plot the boundary conditions as well. So I'm going to give it a variable name, call it T1. And this one is Tn, my last value in the number of points. And then in between, I have T2, T3, all the way to the point before last. These are unknown. I don't know them. I don't know them yet. So all we know now is a bunch of unknown discrete variables and the governing equation. So again, we ask ourselves, seriously, when you are in trouble, when you forget what to do, go back to this question. Is my equation valid at these points? Yes, it is valid. So go ahead and apply it and then discretize it. Okay? So yes, the governing equation is valid at each one of those points. So d2h by dx squared at point 2 is indeed equal to h. Now notice, h times t2 minus t infinity. Okay? So be careful about the indexing here. Same thing for point 3. The second derivative of temperature at point 3 is equal to h times T3 minus T infinity. And so on, okay? For an arbitrary point I, it's HTI minus T infinity. Okay, very good. So now this is our representative equation because I can go from 2 to n minus 1. Okay? At the end points, I don't need this equation because I have known values. I don't have a degree of freedom there. I know the values T1 and Tn and T right. So now we approximate the derivatives Okay, well, guess what? We kind of learned that. If you don't remember it, go back to that slide where I have the list of derivatives. This is simply the second derivative. It's a central approximation. It says that the second derivative at point I is this kind of balance between temperature at I minus 1 minus twice the temperature at I plus the temperature at I plus 1. So you're saying there's this contribution from this temperature, and this temperature to the slope, to the second derivative over here. Okay? And that's equal to h Ti minus T infinity. Okay, wow. We did a lot. You might not see it yet, but just wait for the next slide. Now we have a relation. Okay, a relation. I have to make this joke in my CFD class because I always get YouTube comments on it. We say we have a relation between terms, not a relationship between terms, because mathematical terms are not persons. So we have a relation between the terms, not a relationship. Okay, so we have a relation between these different terms, and it gives us some formula between T1, T2, T3, and so on. If I were to take this equation now, which is valid at every one of those points, and apply it here and here and here and here and here and here, I'm going to get a system of equations that connects all of those points together. Okay? So first, let me clean it up a little bit. If I multiply by delta x squared and move the unknowns to the left-hand side and put everything I know on the right-hand side, right? My unknowns are Ti, Ti plus 1, and Ti minus 1. And everything I know is, I know h, I know delta x, I know T infinity, so I put those on the right-hand side. Then I can build my system of equations. At point I equal 1, I know that T1 is equal to T left. At point 2, I know that T1, so take I equal 2, plug it up there. I have T1 minus 2 plus h delta x squared times T2, I equal 2, plus T3 equal minus h delta x squared T infinity, right? Okay, great. So we know T1, that's okay, but we're trying to solve for T2 and T3. So what's the equation for T3? We go to point 3. It gives us an equation that connects T2, T3, and T4, and so on and so forth, all the way to the last point. Now, what is this? Okay, so it's a system. Yes, it's a matrix. But what does a matrix represent? It represents a system of linear equations. Whenever you hear the word linear, you should rejoice because you can solve it very quickly, right? Very easily. This is a system of linear equations. Why are they linear? Because our unknowns show up in a linear fashion. That's kind of tautological, right? So our unknowns are not squared or multiplying each other. They're not under the sine function or a cosine or an exponential or transcendental. They just show up as a coefficient, just like you write a system of equations. Ax plus by equals c, and dx plus ey equals g. That's two equations with two unknowns that are linear. This is the same thing. Coefficient times T1 minus plus coefficient times T2 plus coefficient times T3, coefficient times T2, coefficient times T3, coefficient times T4. Oh, where's the 1 for 4, and so on. For it to be well posed, you need to have as many equations as there are unknowns. Do I have that? Absolutely. I have technically n minus 2 unknowns. Okay? But let's say we are going to include these 2 points which we know. So I have n unknowns and n equations. They're all linear? Yes.
So at the endpoints, we know the temperature, right?
Yeah.
Is it also we know the temperature at every single point of time, or just?
We haven't touched on time yet. Okay. So this is a steady state example. We're going to add time next. Okay. But typically at the boundary, your boundary could be time dependent or could be fixed in time. So we'll be able to handle both cases. Okay. All right. So the first thing you do when you have a system of linear equations is write it in matrix form, because matrices are beautiful. They simplify your analysis significantly. And if you've done your linear algebra, this is what it looks like. You write in a system of linear equations, you first define your vector of unknowns, which are T1 all the way through Tn over here, right? So this is your solution vector. Your matrix represents the coefficients of these equations, right? So the first row in your matrix, whenever you think about matrix, and I tell this everyone, a matrix is meaningless. Whenever you see a matrix, always think system of linear equations. A matrix doesn't exist alone like that. Oh, this is a matrix. But it represents something. and always it represents a system of linear equations. So a matrix corresponds to a system of linear equations. Okay? It will have properties and cool things about it, etc., but it always corresponds to a system of linear equations. Okay? The rows in these equations, in this matrix, they represent your equations at all points. So the first row is your equation at point 1, which is 1 times t1 plus 0 times t2 plus 0 times t3 and so on. So it's really 1 times t1 equal t left. Yes, exactly what we expected, right? The row number 2, it corresponds to point number 2, the equation at point number 2, which is t1 minus this times t2 plus t3 equal, etc. Indeed, this is 1 times t1 minus 2 plus h delta x squared times t2 plus 1 times t3 plus 0 times all the other ones equal to minus h delta x squared, and so on. Okay? This should be a square matrix, and it will be invertible. It should be a square matrix because you have as many unknowns as there are equations, as many equations as there are unknowns, right? And hopefully it's invertible. If you did things right, the process is physical, it's going to be guaranteed to be invertible to find a solution. Okay, are we ready for some coding? So we're going to code this up in Python. Okay? Now, my numerical methods folks, they know how to do this very, very well. All right, so they're going to help me out today as we walk around and do this. But first, I want to give you some tips if you haven't used Python before. So in the SAD universe, we use something called Pythonification. This word is defined as turning everything into Python. Okay, we even have a T-shirt and a mug with the definition Pythonification. It's the conversion of a mathematical formula or abstract concept into code using the Python programming language. It's also the interpretation of everything in life as though through a Python lens. So when sitting at the dining table, Josh said, from kitchen, import dishes. For dish in dishes, place dish in front, and his mom interrupted, just stop Pythonifying dinner, please. Anyway, so, okay. So as we Pythonify this, so we're going to turn this into Python code, okay? Sorry for the lame jokes, but, you know, they still resonate a little bit. It's funny, okay? I had a comment in my student feedback in numerical methods that said, the best part was when Professor Saad used to say these jokes that were so lame and everybody was silent, which made them even funnier, and everybody laughed because they were so lame. I guess, you know, when you become a dad, your jokes become the lamest. Okay, so if you notice, if you look at this matrix, this system of equations, everything is zeros except for the main diagonal, the first upper diagonal, and the second and the first lower diagonal, right? There's non-zeros on the main diagonal. There's mostly ones on the first upper diagonal except this guy. And there's mostly ones on the first lower diagonal except this one, okay? Everything else is zeros. So we need a mechanism. This is called a tridiagonal matrix, okay? Because only the primary 3 diagonals are non-zero. Okay, and it's a characteristic of diffusion processes. You will see when we take this to 2 dimensions and 3 dimensions, you get pentadiagonal matrices, so you get like these bands of non-zero diagonals, okay? So we need a mechanism in Python to easily program matrices that look like this, mostly same coefficients everywhere, on a few diagonals, and everywhere else is 0, okay? And so thankfully, most entries are repetitive, okay? Now, by the way, this is only valid for structured grids. For, you know, when you go unstructured, it becomes a little bit more complicated than that. Okay, so the plan is, if we can create one-dimensional arrays or vectors for the diagonals, so we create a vector here, a vector for this one, and a vector for that one, and somehow tell Python, put them in a matrix, that would be a smart way of doing it. Rather than creating a 2-dimensional array or matrix and going through every point and putting in a value, that's not efficient, okay? A cleaner way of doing it is just building these as one-dimensional vectors and placing them somehow in a matrix, okay? Everything else is 0. All right, so step 1 would be to create one-dimensional arrays for the non-zero diagonals. In Python, and again, if you haven't seen this before, that's okay. We're going to program it together. You'll get to see it. In Python, in the NumPy library, which is going to be fundamental to us. This is shown here as NP, and you'll learn where that comes from. There's a function called ones. It gives you an array with values of 1 in it. What is the size of that array? Is n. So if you want to create an array of ones that is of size 3, you say np.ones 3 gives you 1, 1, 1. An array of ones of size 5 you say np.ones of size 5 gives you 1, 1, 1, 1, 1. Okay? Great. So now to create non-trivial values, so we can use this to set the first upper and the first lower diagonal. And then we go and fix this last point and fix the first point, okay? What about the middle? You have -2s mostly. So to create the non-trivial values, simply multiply numpy.ones by whatever value you want. Okay, so if you want the -2, you simply say, my main diagonal is -2 times numpy.ones of size 5. It's going to be -2, -2, -2, -2, -2. Okay. Then you go and fix the first and last values. D0, which is the first value in this main diagonal. Python, we index from 0, unlike MATLAB. So the first entry in this main diagonal, I want to change it to 1. So I say D0 equal 1. So that changes that first value. Okay, so it takes this, changes this value into 1. Okay, now this is what's cool here. To change the last value, I'm going to say D minus 1 equal 1. What the heck does that mean? Python arrays are cyclical. You can index forward and you can index backward. You can index from 0, 1, 2, 3, or you can index backward, -1, -2, -3, which is great. Because I don't need to know the size of the array to be able to access the last point or the second point from last. All I need to do is D minus 1, D minus 2, D minus 3, and I can access the endpoints, okay? So I have some sample code here, but we're going to do this together. Okay, and then you combine them to build the full coefficient matrix. So now we have our individual vectors. They're 1D arrays. They're not matrices, okay? They're just simply 1D arrays, okay? To combine them together, we use another function in Python called diag. So diag takes a 1D vector and places it on the kth diagonal in a matrix. The main diagonal is by definition at location 0. First upper is at location 1. First lower is at location -1. Second upper is at location 2. Second lower is location -2, okay? Who's seen this before? Okay, good. All right, so K0 is main diagonal, K1 upper diagonal, etc. So we're going to take D and put it at 0. And we're going to take upper diagonal, put it at 1, and lower diagonal and put it at -1. And then we have our full matrix. Yes? Pardon me? Yes, yes. For the remaining, it's all zeros. Yes, it's all zeros. OK. All right, I have a little warning here. Never mind that. OK, so let's go ahead and do this in Python. So grab your Jupyter notebooks. OK, we'll probably just do this example today. But we'll go faster next week, OK? Next Thursday, on Thursday. OK. So I'm going to open up a Jupyter notebook. And going to do a new notebook. OK, I'm going to be very brief in my notebooks. Ideally, I always say that you need to be very expressive and descriptive in your notebooks. Talk and explain what you're doing. But in the interest of time here, I'm just going to focus on code. But in your notebooks, my advice to you is write about what you're doing, because a week later, you're going to forget what you're doing. Sometimes I come back to these notebooks and I'm like, what was I doing here? Like, seriously, I don't even understand, like, past me, right? So put notes, take notes. And that's why we have Jupyter Notebooks, because with Jupyter Notebooks, you can combine text and mathematics, OK? Who's used notebooks before, Jupyter Notebooks? OK, more or less. All right, good.
The only thing I haven't done is adding text and writing equations and stuff.
OK. OK. So yeah, you can convert the cell. You can convert the cell type to a markdown cell. And markdown is simply text. It's a kind of text language, okay, in Python. So, and it has a shortcut. So remember these two shortcuts, Y and M. They might be different on your computer, but Y and M is the way to toggle between cells from code to markdown. By default, a new cell is always code, and you see this in with a bracket in it, like give me input. Okay. If I press the letter Y on my keyboard, okay, or actually the letter M in my case, and if you have a PC, it's probably Y. So if I press M, it turns it into text. So now I can write text here. And then if I press Shift Enter to run it, it turns into text. Okay, so if we say, okay, we want example 1, steady state heat equation in 1D. Okay, and I want to make it a nice big title. Look at that, turns into that. And then you could say, all right, in this example, we solve the following steady state equation. Right, now you can write math. And what do you do for math? Use LaTeX. Begin equation, then end, just like you do any LaTeX. If you haven't done LaTeX, you should learn it. And I say math Rm, okay, d2t by dx squared is equal to h times t minus t infinity. Okay, look how beautiful that is. Okay. Now notice I put math Rm on the derivative because the derivative should not be italicized. The derivative is not a variable. It's an operator. Don't italicize operators, okay? Like don't write the sine function as sin in italics. Those are variable names, sin. So write it as \sign. Anyway. Okay, let's get to coding. Hopefully we can do it in the remaining 20 minutes. All right. What I'm going to write here is what I call my boilerplate. Okay? See, what I taught in numerical methods is really getting you ready for graduate CFD, right? So, okay, what is my boilerplate stuff? Is import NumPy, import matplotlib, clean up matplotlib so it produces beautiful figures, and that's it. Okay? So what I'm going to write here is going to be your template for every notebook that you will use from here onwards. You just copy paste that code into each and every notebook, and you'll have all your libraries ready for you to use. So we will need NumPy. Let me see if I can zoom in a little bit here. So we will need NumPy as the Python numerical library. So that gives us really nice arrays that we can operate with. Okay? So all I have to do is say import NumPy. But instead of calling the word NumPy every time I want a NumPy function, I'm going to give it a nickname. And that nickname is going to be NP, as what people use, okay? As NP, okay? Import NumPy as NP. All right. Now, I also want to import plotting capability. Import matplotlib.pyplot as PLT. So again, matplotlib is the big master plotting library in Python. pyplot is a special Python plotting library from matplotlib, and that together as I give it a nickname called PLT for plotting. Okay? Okay, and that's it for now. All right? Okay, so now let's set up some definitions for our problem. My length of the domain is going to be 1, let's say 1.0. So in meters, this is length of the rod, okay? And it's going from 0 by definition, right? And I'm going to put 100 points. Let's say you can do 200, you could do 300 points, doesn't matter. Okay, next I want to let's define the x-axis or the abscisses, okay? So x values, I'm going to need those because I want to plot the temperature versus the x values. So I'm just not going to plot the temperature versus 1, 2, 3, etc. I want to plot it versus the actual location on the rod. So I'm going to create this set of discrete points that I told you we're going to discretize the rod in. Turns out there's a really neat Python function called linspace. And it also comes from NumPy. And it goes as this, linspace. And you give it a start, an end, and how many points you want. Okay? So now here's some tips. If you forgot what a function does in Python, open parentheses, okay, and close them, and press Shift Tab. So when you press Shift Tab, it gives you the signature of the function, or, excuse me, how to use the function. So this is telling me linspace needs a start and stop, and then a bunch of other things here. Whenever you see an equal sign in the function signature, it means it has a default value. Okay, so if the least amount of info I need to give to linspace is the beginning and the end. It automatically populates those last variables. Okay, but I want to begin at 0 and at 1, but I also want to specify the number of points. Okay, so I'm going to put 100 there or whatever. Right. Now, if you scroll down, it explains everything for you. You know, start, stop, num, endpoint, etc. So I'm going to go from 0 to L. Okay, from 0 to L with endpoints. Okay. Now you're confused. What does linspace do? What does it do? Just print it out, man. Just print X. It's a lot of values. Well, at least they start at 0 and they end at 1. Okay, are they correct? Maybe not. Let's do 5 points and see if that makes sense. With 5 points, oh, look at that. 0, 0.25, 0.5, 0.75, 1. That's consistent. If I put 5 points on the rod, those are going to be the coordinate, the abscissa for those points. Okay? So when in doubt, print it out. Okay, we also have a T-shirt for that. Okay, 100 points. Okay, great. All right, so now, because this is equal spacing, that also defines delta x for me, right? What is delta x? It's simply the difference between any one of those two values in the x array. Now, this x is an array. It's a NumPy array of size 100. So again, if I print x, this is an array, okay? It's an array of values starting 0, etc. So x0 is the first value, okay? x1 is the second value, and so on and so forth. Now, the difference between any one of those 2 points is my spacing, my grid spacing, because they're equal. So I'm going to do x1 minus x0. So that gives me my delta x. Again, if you're in doubt, print it out. Okay, yep. Delta x is 0.01, 01, 01, etc. Okay, great. You can put 101 points to make it cleaner. All right. Okay. Let's define a few more quantities. We want h, which is... So sorry, I don't have the slides next to me. Should have a nicer way of putting the slides here. Let me move this. Okay. So if you look at what we're trying to do here, where's the cursor? Okay, there he is. Okay. So we're just trying to program this system of equations, okay? So I still want h. I already have delta x. I want h, and I want t infinity, and t left and t right. Agreed? Okay. So h, let's say 0.1, whatever. Again, we're gonna check later that if h is large, the heat transfer is gonna be much more equal everywhere with T infinity. If h is small, it's gonna be very hard for T infinity to distribute that heat across the rod. Okay. So we start with some value h. I don't care what it is. T left, what do you want it to be? 200 kelvins, okay? And T right, let's put it at 300, okay? And T infinity, let's put it 500. So you have a hair dryer. Maybe not there, like burn your hair, 500. Well, I don't feel that because it will burn my scalp, I guess. Thank you very much, everyone. Okay. Are we all in sync? All right. Should we start building those diagonals? Let's do it. All right, build the 3 diagonals. We're going to start with the upper diagonal, and I'm calling it UD. And if we remember here, the upper diagonal was mostly 1s, except the first entry, it was 0. Okay? So I'm going to do np.1s. What is the size of the upper diagonal? Okay. 2n minus n minus. No tricks. Okay, so let's think about this. How many equations and how many unknowns do I have? N equations and unknowns. So what is the size of the matrix? N by n. Okay, how many entries on the diagonal? N entries on the diagonal, on the main diagonal. Good. Upper diagonal, n minus 1. Lower diagonal, n minus 1. N minus 2, n minus 2, and so on. Okay? Good. Always go back to the number of equations, because when we get in 2D, this is going to be nasty, because the size of the matrix is going to be nx by ny times nx by ny, where you have x and y dimensions, right? So it would be n squared by n squared, not n by n, right? So it's going to be something different. So for the upper diagonal, it's n minus 1. Okay, if you're in doubt, print it again. So print UD. Oh, yay, it's all 1s. Okay, but I want the first entry in UD to be 0. So I'm going to access that first entry at index 0. So UD0 is going to be 0. So when I print this, indeed, my first entry is 0 here. Okay. So that is our upper diagonal. Diagonal. Okay. Lower diagonal. Also np.1s of size n minus 1. And for the lower diagonal, the last entry was 0, right?
Sorry, 1 second.
Yes.
Did you change your n to 101? Or
It doesn't matter. Keep I changed to 101. You can do 200. You can do 7. Yeah. I changed it to 101 because I wanted delta x to be nice. Sorry, print dx here, 0.01 instead of a very long number. Okay. Lower diagonal, same thing. But the last entry in the lower diagonal is 0. So LD, last entry, which I can access by reverse indexing from the back, equal to 0. And then main diagonal, MD, it's mostly minus 2 plus h delta x squared. Okay? So it's going to be minus into 2 plus h times dx times dx. Okay? Times np.1s of size n. The first and last entries of the main diagonal are 0 and 0. They're 1 and 1. Okay? So MD0 is 1, and MD at the end is 1. Okay? Again, you're doubtful, just print it. Okay? Change the number of points to something you can see. Put 10 points or 11 points. Okay, and then print them all. So, okay, print the main diagonal, print MD. It's going to have a bunch of values. Look at that, minus 2.001, et cetera, et cetera. Okay, good. Seems consistent. Okay, so now let's build the full matrix. Let's build the full coefficient matrix. And I'm going to call it A. A is np.diag for my lower diagonal, which is located at negative 1. That's the first lower. Plus np.diag for the main diagonal, which is located at in reference 0. Plus np.diag, which is located for the upper diagonal, which is located at 1. Okay, and let's print A. Okay, it looks pretty nasty because there's a lot of points, right? So we can change the number of points. Let's put 5. Look at that. Okay, it's got 1 on the main diagonal, and then minus 2, same number. Last entry is 1. First upper 1, 1, 1, 0. First lower 1, 1, 1, 0, and everything else is 0. That's pretty neat, right? That's pretty neat. automatically does that for you.
So your upper and lower diagonal, you have index is 0 and then it's 1.
Yeah.
And your main diagonal is 0 also. So is that telling you where the diagonal is?
Yes, so the main diagonal is the reference counter. It's always at 0. The main diagonal is located in this diag function. The main diagonal is always located at 0. First upper is located as 1. First lower is -1. Second upper is at 2. Second lower is -2, and so on.
How come your upper diagonal index is 1? And
Upper diagonal here is 1. And lower diagonal is -1, right?
oh,
Well,
there it is.
yeah. I start with the lower diagonal. Yeah.
Oh, I see. So you're saying, okay.
Yeah. You can change the order here however you like, right? Doesn't matter. We'll always give that same answer. Okay? Give you a second to catch up. That's fine. The next step is going to be to build the right-hand side, and then we're done. So let's go ahead and try to build the right-hand side. I'm going to call it RHS, and it's going to be, it's mostly minus h delta x squared t infinity, right? So right-hand side is mostly minus h times dx squared times t infinity times mp dot 1s of size n, because there are n equations, right? So there's n entries in the right-hand side, size n. And then I need to fix the first and last entry in the right-hand side vector. Right-hand side 0 at 0 is, remember, t left, and the right-hand side at the end is t right. Okay? Now, when we go to 2 dimensions, we can use a similar procedure to build the matrix in 2D, but there's also another way in 2 dimensions to do it. Okay, I will teach you both ways, but this one is kind of nice and neat because it comes in always handy when you have a repetitive matrices to use this approach. We're done. Okay, we're done building the right-hand side, the coefficient matrix. Print the right-hand side. Okay, so now we're ready to get the solution. So I'm going to go back to 101 points. Okay, so now how do we solve this system of equations? I promise you one day in this course we're going to get into the theory of iterative solvers, and we'll talk all sorts of multi-grid, etc. But for now, my objective is to get to solve Navier-Stokes. So I'm going to use a prepackaged solver in Python. All right, the first one we will use comes from the linear algebra library from Python, okay, which is called linalg. Right, it's very simple. You call numpy.linalgebra.solve. Couldn't be any kind of more intuitive than that. Now, what is numpy.linalgebra.solve? If you press Shift Tab, it tells you solves a linear matrix equation or system of linear scalar equations. Okay? So now the format for this is A, comma B. What is A and B? A is the coefficient matrix. B is the right-hand side. Comes from AX equal B. Okay? So our coefficient matrix is A. Our B is right-hand side. And I'm going to store it in a variable, call it sol for solution. You run this, doesn't give you an error. That's a good sign. First thing you do is plot it. So we're going to plot our solution versus location on the rod. So plt.plot. On the x-axis, I'm going to place what? My x vector of values. Right? On the y-axis, I'm place my solution. And if things went well, I should see some curve. Okay? All right, I'll wait for you to catch up. You guys got it? Amir, you got it? Okay. Well, you did it just last semester, right? You've done it like 10 times for a homework, actually like 70, 80 times, right? For each homework assignment. Okay. Okay, this is a solution. Okay, victory, but not yet, right? So we need to make sure that the solution makes sense. The first thing I like to check is visually inspect my solution, make sure it looks physical, and that at least it satisfies my boundary conditions. Does it? Yep. My left temperature was 200. My right temperature is 300. Good. What is it doing in the middle? Looks like not much. It almost seems like it's a straight line. Okay? So when you think about it, if the right-hand side is 0, what is the answer, the exact solution for the second derivative? It's a straight line. If you have d2t by dx squared equals 0, the exact solution is t equal some alpha x plus beta, right? It's a straight line. Indeed, so this tells me because my right-hand side is so small, it's barely having any influence on that solution. So goes back to t infinity and most importantly h. So let's beef up h. Okay, so let's immerse this rod in a fluid that has a much higher heat transfer coefficient, boiling oil or lava or something like that. Okay, so let's go wild. Let's go h equal 100. What should we expect? Temperature at both ends is going to still be anchored there because those are boundary conditions. We're still going to see 200 and 300. What's going to happen in the middle, that curve should start approaching t infinity. It cannot go above t infinity because once t hits t infinity, the right-hand side becomes 0. No more heat transfer. Right? It just goes through. Okay? So let's see what happens. So that's what I expect. I expect temperature to be anchored in the middle and there's some bulge at the ends. Temperature is fixed and a bulge in the middle. Okay. Yes. I spent my time talking and explaining. All right, so let's see it. Oh, look at that. And look at it. It's trying to reach t infinity, which is 500. It's still anchored at the endpoints.
But now my computer died.
Oh, sorry about that. Bummer. Well, we're almost done. So we're actually done. But let me just drive this last couple points home. So yes, this looks great. If you keep driving h higher, physically, yeah, if we get to 1,000, that's just going to be flat at 500. So look at that. It's going to be flat at 500 because that fluid that is passing on t infinity to the rod is doing so effectively, and it's balanced by whatever conduction there is in the rod. It's just distributing that heat almost very quickly everywhere. But it still has to drop to 200 and 300. When h approaches 0, what are you going to get? A straight line. Okay, so if you go to 0.001, for example, or even 0, you're going to get a straight line. Because then that governing equation becomes becomes d2x by dx squared equals 0, whose solution is alpha x plus b, which is a straight line. Okay? Yeah, just simple. Yeah, conduction, no source terms, essentially. Yeah. Okay? All right, I think this is good for today. On Thursday, we will add a time derivative to this problem. Okay, and see how that temperature evolves over time, which is what like everybody in numerical methods was anxious about doing. It's not that hard, okay? All right, thank you everyone. Hope this was useful.